The topics for this video are imaginary numbers and absolute value. So we know a lot about real numbers. Now we're going to introduce imaginary numbers and complex numbers. So an imaginary number, we define the imaginary number I as the square root of -1. If we square I, that's squaring -1, and what we're going to get is -1. So if we multiply I with itself, we get -1. If we cube I, this is the square root of -1 cubed, which is the same thing as the square root of -1 squared times the square root of -1, because I have two of these and one of these. And this is -1, as we just saw, because this is I squared. And this is just I. So that tells me I cubed is equal to -I. Another interesting fact about imaginary numbers is if you raise it to the fourth, the number I, this is -1 to the fourth, which is the square root of -1 squared times the square root of -1 squared. This is I squared times I squared, and I squared is -1. So we get -1 times -1, which is a positive 1. So I to the fourth is 1. So let's look back. I is the square root of -1. If we multiply I with itself, we get -1. If we cube I, we get -I. And if we raise I to the fourth, we get 1. And what's really fun about these imaginary numbers is if you raise I to any power, let's say we raise it to the 8th power, what we can do is we can break it into multiples of I, or we can make it a -1 or a 1, depending on what the power is. So watch this. I to the 8th is the same thing as I to the 4th times I to the 4th, right? Because 4 plus 4 is 8. But now we know that I to the 4th is 1. So this is 1 times 1, which is 1. So I to the 8th is equal to 1. Now you can choose something else. You can go with, let's say, I to the 11th. This is equal to, I like to break it into multiples of 4. So it's I to the 4th times I to the 4th. That's 4 plus 4 is 8. 9, 10, 11, 12. We can't do I to the 4th. We can do I cubed. So this is 4 plus 4, 8, 9, 10, 11. So this makes 1, this makes 1. And I cubed we know is -I. So then this is just -I. So any power you put on this I, if it's a big power, you can always reduce it to either 1, -I, -1, or just positive I. Okay, let's talk about complex numbers. Now, complex numbers take this form: A plus BI, where A and B are real numbers. Now, what are real numbers? So think of integers, so things like, just to review, so real numbers can be anything like 0, 1, 2. We can put -1, -10, any of the negatives. Also decimals like 3.5. Square roots like square root of 7. We can also do things like pi, that's about 3.14. All of the numbers that you're familiar with that make up the real number line. So the x-axis, you know how we have 0, 1, 1, 2, and so on. And we have all the numbers in between 0, -1, -2. So any number on this x-axis. That is the set of real numbers. And the set of real numbers is a subset of the complex numbers. So first I want to show you some complex numbers, just to give you an idea of what we're looking at here. So some examples of complex numbers. Now remember, they have to take this form a plus bi, where a and b are real numbers. So we could have something like 2 plus 5i. That's a complex number. The real part of this is 2, and this is called the imaginary part because it's stuck with this letter I. We could also have something like 7 minus 10i. This takes this form, a plus bi. Here the a is 7 and the b is negative 10 because it's the same thing as 7 plus a negative 10i. Now, something else we could have is we could get rid of this piece because we can make it a 0 because 0 is a real number. So 7 plus 5i, or just 5i, that's a complex number. We could also make the imaginary part 0. So we could have something like 3 minus 0i, which is the same thing as 3. So in fact, with this definition of complex numbers, when we let b equal 0, we get all the real numbers. So the real numbers are a subset. You could think of, if this set right here has all the real numbers in it, then the complex numbers is a set that's bigger. It's bigger than the real numbers. It contains the real numbers and extra stuff, and the extra stuff it contains is this imaginary part. Something else that is a complex number would be something like 9 minus the square root of 3i. Now, square roots are real numbers, and so it takes that form a plus bi. You could also do something like pi minus 12.5i. So as long as this number and this number, they're both real numbers, then you have a complex number. And again, this piece right here that does not have the I associated with it is called the real part of the complex number. And then this piece that's attached to the I is called the imaginary part. So what you're going to see in pre-calculus is we're going to be finding roots of quadratic functions. And we've done this a little bit already. We know how to find some roots. For example, let me scoot this down a little bit. When we had a quadratic function like f of x is x squared minus 1. How we found the roots, remember the roots are the x-intercepts or the zeros of the function. What we would do is set this function equal to 0. And you could solve this a few ways. So you could factor it, or you can move the 1 to the other side. So you have 1 is equal to x squared, which tells you that x can be plus or minus 1. And if we were to graph this, we know that this is the parent function x squared moved down 1 unit. So the graph looks like this. And these 2 points where we cross the x-axis are called the zeros, or the roots of the function. And they would be plus or minus 1. So this one would be negative 1 comma 0, and this one is 1 comma 0, this point here. But we also saw some functions like g of x is equal to x squared plus 3. And if you set this equal to 0, and then move the 3 to the other side, you see that you have something being squared, giving you a negative number. Now, there are no real solutions to a graph like this. If I graphed it, what would this look like? Well, this graph G is the parent function shifted up 3 units. So it would look like this, and you can see it doesn't go through the x-axis. So it has no real solutions. This is not factorable. And if we took the square root of both sides, well, if you put it in your calculator, you would get an error. And that's because your calculator only deals with real numbers. Now, what we're going to do is we're actually going to take the square root of both sides, so we get x is plus or minus the square root of negative 3. And we're going to think of the square root of negative 3 as the following. the square root of negative 3 is going to be the same thing as the square root of 3 times the square root of negative 1. And what we can do from here is we define the square root of negative 1 as I. So what we're getting is the square root of 3 times I. So x is going to be plus or minus the square root of 3 times I, like that. And we're always going to put the I in the back. You could put it in the front if you wanted to. If you wanted to say plus or minus I square root 3, that's fine as well. I'm just going with that form a plus bi. Here the a, the number in the front, is 0, and we have square root 3 as your b. So you have two solutions to this. And what's interesting about this is we said that this wasn't factorable, and it's not factorable with regards to the real numbers, but it is factorable with regards to the complex numbers. So x squared plus 3 equal to 0 is going to be x plus the square root of 3i times x minus the square root of 3i. That's how you can factor this. And let's do something interesting. Let's FOIL this and see if we get this here, x squared plus 3. Now, how I got this piece here is, remember what we did when we had x-intercepts. Well, x-intercepts say that when we factor this, we'll have x plus one of the intercepts and x minus one of the intercepts. So let's FOIL this. What would we get? We would get x times x, which is x squared, and then we have an x times a negative square root 3i, and then we have an x times a positive square root 3i, and then this last piece is minus this one times this one, because I have this minus here, so I get the square root of 3i squared. And we're setting that equal to 0. And that's just FOILing this out. And then you can see what I have here, minus x square root 3i, I have that here as well. So those cancel, because I have a minus and a plus. And then if we square this piece, we get x squared minus square root of 3i squared is equal to 0. And remember, if you have two things being multiplied and if you want to square them, you can square each piece. So here I have, this is my a and this is my b. So this is the same thing as x squared minus the square root of 3 squared times I squared is equal to 0. And then from there, you can see that you get x squared minus square root of 3 squared is 3, and I squared is negative 1. So we get x squared plus 3. And so it did factor, like I said right here. Factored into x plus square root 3i and x minus square root 3i. So what I want to focus on, and I want to do some problems involving simplifying radicals and writing square roots of negative numbers as a complex number. So we're going to have an imaginary part. So let's see if we can do that. I'm going to give you, you can see I have 10 problems. You should pause the video and write down each problem and watch me do a few and then see if you can do the rest and double check to see if we can get the same answers. So here are the first 8. And here are the last 2 problems. Okay, so remember, a complex number is a real number plus an imaginary number. And these imaginary parts and real parts can be 0. So if we just get a real number, that's okay. That is a complex number. So we're starting with number 1. What is the square root of 9? Well, that's easy. It's just 3. So that is our complex number. What is the square root of negative 9? Well, this is equal to the square root of 9 times the square root of negative 1. We can break a square root like this. So this is just 3 times the square root of negative 1, which we're saying this is I. So this is 3 times I, or just 3i, like that. You have to be careful with where the negative is. And I notice I put negatives in all different places because I wanted to see if you understood what the negatives, like what determines when we have I and what determines when we just have a negative, like a negative number. So this negative is outside the square root, and it's going to stay outside the square root. This is the negative of 3, because this piece is 3. So your answer here is just negative 3. So when the negative is on the outside of the square root, it stays a negative. When the negative is in the inside of the square root, it becomes an I. Here I have a negative on the outside and the inside. So this is the same thing as negative. Now let's focus on this part here. So this negative stays on the outside. This part is the square root of 9 times the square root of negative 1, which we said this was I. And then we have this negative that we have to pull down. This becomes 3. So you see you get negative 3I. And that's the solution to this one. Okay, let's move on. The square root of negative 16. So this is the square root of 16 times the square root of negative 1, which is I. So let's cross that out and just put I here. 16 is a perfect square, so this becomes 4I. Now this is something you might see in the pre-calculus class. You can see that you have to simplify this. This is not a perfect square, but we're going to break it up as much as we can. Notice that this is the same thing as the square root of 25 times the square root of 2, because 25 times 2 is 50. And this is a perfect square. And this can't be simplified any further, so this is 5 root 2. And there's no negatives anywhere, so this is just a real number. But here I took the same thing and put the negative on the inside. So this is the square root of 25 times the square root of 2 times the square root of negative 1. I'm just breaking it into its factors. This becomes a 5 again, and this is an I, and we leave the square root 2. So this is 5 root 2 times I. And remember that I does not go into that square root. Be careful about that. The square root ends on the 2. How about this one? 10 is the same thing as 5 times 2. And if you have the square root of 10, this is the square root of 5 times the square root of 2. And neither one of these are a perfect square. So you can't simplify this. You can't take anything out. So the only thing that we can do to this is we can make it the square root of 10 times the square root of negative 1. So in that case, this just becomes 8 plus the square root of 10I. Okay, let's look at the last two. I have 4 minus the square root of negative 49. Let's do that piece up here. The square root of negative 49 is the square root of 49 times the square root of negative 1. And this is a perfect square. So this is 7I. So we're going to substitute 7I into here. But notice I have a 4 minus. So this becomes a 4 minus 7I. And then for the last piece, I have 3 minus the square root of negative 120. Okay, let's try to break this up, and then we're going to replace it. So the square root of negative 120 is the square root of 120 times the square root of negative 1. That becomes I, so let's put it right there. Now the square root of 120, you want to figure out what the perfect square is. I know that 120 is 12 times 10. Okay, now that didn't get me very far, but let's see if I can break it even further. Now that is 4 times 3, so then we have 4 times 3, and this is 2 times 5. Well, 4 is a perfect square. So I have, this is 2 times 2, so I can take one of those out. So 4 becomes 2 when I take it out of the square root, and I have 3 times 2 times 5, I. Okay, and so I can't take anything else out because none of these are perfect squares. You can't multiply these numbers together to get something that's a perfect square. So then we're just going to leave this under the square root, and we're going to multiply these numbers together, which is 30. So that is 2 square root 30I. And that needs to replace this piece. And I'm going to put this in a different color so we can see what this final solution is. This is 3 minus 2 square root 30I. So all I did was replace this with this piece here. And again, that I does not go under the square root. So I think we've got some good practice with this. Let's move on to absolute value. Okay, I have, looks like 9 problems. I think absolute value you've seen before and you should be familiar with it. We're going to go through each one of these problems. Maybe take a minute and copy them down. So here are the first 4. Put a little bit of space. Here are 3 more. And then here are the last 2. Okay, so let's start with this first one. It says the absolute value of x is equal to 7. So what we're doing is we're looking for all values of x, that when I plug them into the absolute value function here, I get 7. So remember what absolute value is. It takes, if you give me a number, I'm just going to take the positive of that number. So for example, if you plug in 5 into the absolute value signs, I just give you 5. If you give me any positive number, I'm going to give you that positive number back. If you give me 0, I'm going to give you 0. But if you give me something negative, I'm going to get rid of that negative and just give you the positive of it. So if you give me negative 19, I'm going to give you 19. Okay? So what numbers can I plug into this and always get 7? Well, x can be 7, because if you plug in 7, I'm going to return 7, and also negative 7, because I'll return 7 when you plug in a negative. So what you're going to do is whatever you see here, you're going to say x is equal to that number, and then x is equal to the opposite of that number, so the negative of it. So like this one, x is equal to 0, and x is equal to negative 0. And negative 0 is just 0, so we don't really need that piece. So the only solution for this one is 0. It's the only number you can plug in and get 0. How about number 3? X is equal to 1. What you see, just drop the absolute value signs and also the opposite of it. So those are your 2 solutions here. Plug in 1 or negative 1, and I'll spit out 1 if I'm the absolute value. This one's a little bit of a trick. Here I say, give me a number, and I'm going to spit out a negative. Well, the absolute value never spits out a negative. It always gives you a positive number. So this one has no solution, because if you plug in negative 6, you're going to get positive 6, and if you plug in positive 6, you're going to get 6. So there's nothing you can plug in there. Okay, I'm going to erase these pieces so I don't see them while I'm working on my next portion. Okay. So we're getting a little more complicated. This one says, I'm looking for all numbers that when I plug them in, and I take their negative, I put them in the absolute value, it spits out a positive 3. Now, the idea is always to get the absolute value by itself. So here, if I had a number on the outside, I would want to get rid of that. But whatever you have here, you're going to take what you see on the inside and set it equal to this and also to the negative of it. So we're going to have negative x is equal to 3 and negative x is equal to negative 3. So divide by a negative, you get x is negative 3, and divide by a negative, you get x is equal to 3. Let's check to see if this works. Plug in negative 3. Well, we take the negative of that and we get 3. And if we take the absolute value of 3, we get 3. So that works. Okay, and if we plug in 3, we take the negative of that, we get negative 3. Then we take the absolute value, we get positive 3. So both of these work. Here I have x plus 5 is equal, the absolute value of x plus 5 is equal to 3. So we're going to do the same thing. I'm going to say x plus 5 is equal to 3, and x plus 5 is equal to negative 3. So we subtract 5 from both sides. We get negative 2, and we get negative 8. Those are going to be our 2 solutions. If you plug in negative 2, you get 3 into here, and the absolute value of that is 3. If you plug in negative 8, you'll see that this simplifies to negative 3. Absolute value is 3. I always think it's a good idea to double check, because sometimes you can make a simple error here, and you just want to make sure you get the right answer. Let's try this one. So we get x minus 2 is 14, and x minus 2 is negative 14. Add 2, I get 16. Add 2, I get negative 12. Again, if you plug both of these in, you do get 14. Here are my last two problems. I've got the absolute value of 5 times x is 25, and the absolute value of 1/4 x is equal to 3. So we say 5x is equal to 25, and 5x is equal to negative 25. Divide both sides by 5, you get x is 5 and x is negative 5. You can verify that, plug those in. You see that the absolute value will give us 25. For this portion, we have 1/4 x is equal to 3, and 1/4 x is equal to negative 3. Multiply both sides by 4, you get x is 12, and x is negative 12. And that's it. That's all we have to cover today.